Hello everyone, and welcome back to another episode of the Internet Computer Developer Journey. In today's episode 2.6, Motoko Level 2, we're going to be taking a look at the core components of Motoko a little bit further. So in Motoko Level 1, we were introduced to some basic Motoko fundamentals such as data types and actors, but now in Motoko Level 2, we're going to expand on that by taking a look at actor type definitions, how actors can interact and use asynchronous data, actor classes, and then we're going to finish up by looking at an interactive example of using multiple actors within a project. So to get started, we're going to take a look at actor types. So in the same way that objects have different object types in Motoko, actors can have different actor types. To help demonstrate this, let's take a look at an example actor that defines a simple counter. The counter simply increments by a value of 1. And so in this code, we have the actor definition for actor counter. Then we have a variable defined for count, and it initially is the value of 0. Then we have a public shared function called inc, and this is using the asynchronous keyword, and it is going to add a value of 1 to our variable of count. So this asynchronously increments the value of count, and it returns a type of asynchronous empty parentheses. Then this next function is another public shared function. This is called read, and this reads the value of count and returns a type of async nat. And then lastly, we have the public shared function of bump. This asynchronously increments and reads the count value and returns a type of async nat. So this is a very basic example that we're going to use to take a look at the actor type definitions. So from this, we have 3 actor type definitions for our 3 functions. So our inc, read, and bump functions each are shared, and they each return some form of asynchronous data. So these are the 3 members of the actor that correlate to the 3 functions. They each have the modifier of shared, and they each have a defined actor type definition that defines the type that they return, such as async with empty parentheses or async nat. So in this definition, we can see that the shared modifier is used for each of these. This shared modifier is optional in the Motoko syntax, so when you go to author an actor type, you can remove this shared modifier and just use the empty parentheses instead. So now let's take a look at shared functions. Shared functions are So now let's talk about shared functions. Shared functions are accessible through remote calls, meaning that a user can submit a call to that function, and all of our functions in the previous example used that shared keyword. Shared functions return a value known as a future. A future indicates that the asynchronous value is expected to be returned, and in the tutorial further, they can be represented as type F. So a call to await F will suspend any other computation in the origin of the call until F is complete, since it's awaiting the return of that future value. Once that future value of F is returned, the execution of the call's code resumes, and it uses that returned F result, which can either be a value, such as the value of the counter, or it can be an error. A shared function in comparison to a local function is that a local function will block the entity making the call to the function until the function has returned a result. So a local function, when you make the call, it is going to wait until the result has been returned, whereas a shared function will immediately return a placeholder value known as a future, meaning that the value will come back, it's just going to come back asynchronously, whereas the local function is going to wait for the value to come back synchronously. An important note about shared functions and their arguments is that they need to return values that are also of shared types. Shared types are a subset of data types that include shared function references, actor references, and immutable data, but they do not include references to local functions or mutable data. Since interactions with actors are asynchronous, an actor's functions must return types in the form of async t, where t is the data type. So in that previous example, we used async nat, meaning that the function is going to return the async value of nat since it is a shared type. So now let's talk about actors and how they can interact with asynchronous data. So shared functions must be executed asynchronously and therefore must return data types in the form of async type. So to return the result of that asynchronous value, the receiver of the future must use that await expression. So if we go back to that example with the counter, the result of counter.read needs to use the await keyword in order to await the value a and retrieve the asynchronous nat value. So we can take a look at this example where we are defining a as the asynchronous nat that is returned from counter.read, and that nat value is awaiting the return of that a value. So in this, first we return the value of counter.read, and that is retrieved immediately. The code does not wait for the result. And since the code does not wait, the value cannot be used as a nat value yet. So to use the nat value, it must await the result of a and then extract the result as that nat value. And so this second line is not executed until a has been completed, since it uses the await a keyword. And alternatively, these two lines of code can be combined into one asynchronous await call directly, which would read let n nat equal await counter.read. So now let's talk about actor classes. Actor classes provide the ability for a series of actors to be created programmatically. To define different actor classes, a separate classes source file will need to be used, and we're going to demonstrate how to define and import an actor class using the following example, which is going to implement a key value store and map keys of data type nat to values of data type text. And then we're going to have two functions to interact with this data, an insert and a lookup function that is going to be used for interacting with that key value store. To distribute the data, a set of keys defined by k will be partitioned into n number of buckets. And in this example, we're just going to set n as a fixed value of 8. So the set of keys are going to be partitioned across 8 buckets. The bucket index value, identified as I, for the value of k, will be determined by the remainder value of k divided by n, so in this case divided by 8. Then the I bucket will receive a dedicated actor value that is used to store the text values, known as v, that are associated with the keys that are in that bucket. The actor responsible for bucket I is obtained as an instance of the actor class bucket I. So that is a lot of different math and compute concepts. So let's take a look at how this looks in the code. So we're going to take a look at this code that will be stored in a file called buckets.mo. And in this, we're just going to import the nat and map data types. And then we are going to define our actor class called bucket, and we're going to have that n value, which, like I mentioned, is going to be a fixed value of 8, and then that I value for the number of buckets, and both of these are going to be data type nat. Then we're going to have our two types of key and value. The key is going to be data type nat, and the value is going to be data type text. Then we are going to create a map where we map the value of key to the value of value. And then we're going to define a get function that returns the key value pair of key, comma, value. Then we're going to have a put function that updates this map of key to value. So if we describe this further, we are defining a bucket that stores a current key value map in a mutable variable called map, and that contains an RB tree that is initially going to be empty. Then we are going to define the get function, and this is going to return any value stored at k and returns map.getK, so any value that is associated with that key of k. Then lastly, we define the put function, and this is going to update the current map to alter the value stored for k, v. Both of these functions, get and put, use the class parameters of n and I to verify that the key is appropriate for the bucket through the assertion of k divided by n equals I. So now if we want to define an actor using this actor class, we would use a new file called map.mo, and this is going to implement a coordinating map actor that uses this buckets actor class. So if we take a look at this, we are importing the data type array, and then we are importing the buckets actor class from the buckets.mo file. And then we are defining an actor called map. And here we are having n be a fixed number of buckets. In this case, it's going to be 8. We're going to define the values for our key value store again, and then define a data type of buckets, which equals the imported bucket class that we've imported from the other file. Then we are going to define an array called buckets, going to define a get function again and a put function. And so if we take a look at this in more detail, the buckets actor class is imported from the module buckets. The map actor maintains an array of n allocated buckets. For each entry in the array, it is initially a null value, which then gets populated with the bucket actors on demand. When the function get k, v is called on the map actor, the remainder value of key k divided by n, in this case 8, is used to determine the index or I value of the bucket responsible for that key. If the function returns a null value for that index value, that means the bucket does not exist. If the index value does exist, it delegates the key to that bucket by calling bucket.get k, v. When the function put k, v is called on the map actor, the remainder value of k divided by n, in this case 8, is used to determine the index I value of the bucket that's responsible for the key. If the bucket does not exist, the bucket is installed using an asynchronous call to the constructor function buckets.bucketI. When that result is returned, it's going to record that bucket in the array called buckets. And then it's going to delegate the insertion of the key value pair into the bucket by calling the put function of bucket.put k, v. So that is a fairly complex example in order to showcase how to use actor classes. If you want to learn more about actor classes or learn more about actor class management, you can check out the documentation that's linked in this tutorial. But for now, we're going to move on to using multiple actors. And so this is where we are going to start the hands-on portion of this tutorial. Up until this point in our developer journey, we've interacted with a single actor that's defined in the backend canister in our Motoko projects. Now we are going to create a project that is going to use multiple actors. So remember that only one actor can be defined per Motoko file, and a single actor is always compiled into a single canister. So to create multiple actors, we need to create multiple Motoko files and build multiple canisters. So in this example, we're just going to create 2 canisters to demonstrate this multiple actor workflow. And to do this, we're going to create 2 actors that are completely unrelated to one another. We're going to create a character count actor, which is going to take a string, count its length, and then return a bool value, so a true or false, if the total length of the string is divisible by 2. And then we're also going to create a daemon actor, and this is going to create a mock function for starting and stopping a daemon. A daemon is simply a program that runs continuously in the background. That is a pretty universal programming and computing term. The daemon actor is going to assign a variable and print out messages. It's purely for the tutorial's demonstration process. It isn't going to have any actual compute or processing benefits in the background for our project here. It's purely demonstrational. So to get started, we're going to create a new project. I'm going to first navigate into my developer journey subdirectory, and I'm going to make sure that DFX is running. So I'm going to use DFX start clean background. And for me, DFX is already running. So then I'm going to use DFX new. I'm going to call it multiple actors. And so for me, I am using DFX 0.17.0. So I'm going to be given this interactive prompt that is used to select the configuration parameters for my project. If you are using DFX 0.16.1 or older, you won't see this interactive prompt. But for me, I'm going to use this prompt and I'm going to select Motoko for our backend language. And then for our front-end language, I'm going to select no front-end canister. Since we aren't using a front-end canister, we are just going to be using 2 back-end canisters. And then we can also add extra features such as internet identity or Bitcoin, but we won't be using either of those in this tutorial. So I'm just going to select enter, and then I'm going to navigate into this new multiple actors subdirectory. So first we want to configure our 2 canisters in the dfx.json file. So let's go ahead and open up our IDE of choice. I'm going to be using VS Code, and I'm going to open the developer journey folder that I have. I'm going to be opening this multiple actors. I'm just going to open the whole folder, and let's get this put over here. And then in my multiple actors folder, I'm going to open this dfx.json folder. I'm going to close my Explorer. And so we can see that I, by default, have this multiple actors backend canister defined, and I don't have a front end canister defined since I opted to say no front end canister. But I don't want to use this multiple actors backend canister. I want to instead use a canister called character_count. And this is going to be defined as having its source code stored at source character count main.mo. And I forgot a curly bracket up here. And I'm going to put a comma and then define the type of this canister as Motoko. And then we want to define the daemon canister as a second canister and make sure we use that curly bracket. And we want the source code for this to be stored at source daemon main.mo, and that line with a comma, and define the type of this canister also as type of Motoko. And close that. And we're going to need a comma after this second curly bracket. And that looks good. So we'll save that file with Command S. And so now we want to create the directories for these 2 canisters. And so here we are going to remove the source files for those default canisters that were created. For me, I don't have this front end canister created, so I'm just going to be using this backend canister command of rm-r source multiple actors backend. And then we want to create the new directories for our new canister. So mkdir source character count. And then we want to use the touch command to create a new file. and that's going to be our source character count main.mo file. And we want to do that same set of commands for our daemon canister. So source daemon and touch source daemon main.mo. So now if we go back to VS Code and we go to our Explorer and we go into source, we can see we have the two subdirectories, and each of these are going to contain these main.mo files. And these are both going to be empty to start with. So let's start with our character count and our main.mo. And we want to first import the type text from the Motoko base library. Then we want to define our actor character count. And we're going to find a public function called test that takes type text that takes an insert or an input of type text and returns an async Boolean value. We'll use a curly bracket and press enter, and then let size equal text dot size text. So we want to define this variable called size that is going to measure the size of the inserted text or the inputted text. And then we want to return size, and if it's divisible by 2, and so this percentage number is going to divide it by 2, and if there is no remainder, so if it equals 0, and then we are going to add our semicolons and save that. So it's defining the character count actor. It's defining a public function called test, which takes an input type of text and returns an async response of type bool. Then the variable size is defined as the length of the inputted text. And if that variable size is divisible by 2 without a remainder, so if it equals 0, bool is going to return the value of true. If not, bool value false will be returned. So that's going to be our character count canister. Now if we go to the empty file for our daemon canister, we are going to insert the following code. So for this, we still need to insert type text. So let's go here and import text, mo base text. And then we'll define our actor daemon, curly bracket, enter, and then we're going to create a stable variable called running. That's going to equal false. Then we're going to create a public function called launch, which is going to return an async type of text. And if that running variable is equal to true, then we want to use debug show the daemon process is running. So we can see that our stable variable called running is manually set to false. And then this function is going to check if running is equal to true. If running is equal to true, that means the daemon process is running. And then we need a semicolon and a semicolon. Then we're going to define public function stop, which is also going to return async text. And then if running is equal to false, debug show the daemon is stopped. So now we want to deploy these two locally, so we want to make sure that we save both of these files, and then we can go into our command line and we can run dfx deploy to deploy these two canisters, and we can see the code for each of these be installed and our canister IDs be returned. And then we can see the URL for the candid UI for both of these. And so now that we have these two different canisters that have two different actors deployed, we can interact with each canister and their associated actors using the DFX canister call command. So for example, if we want to call our character count, we can use DFX canister call character underscore count, since that's our canister name. And we want to call the test function, and we will pass the text of developer journey into that function, and it's going to return false. So the total length of developer journey is not divisible by 2 without a remainder. And then to test the daemon actor, we can use DFX canister call daemon launch. And we can see that this is going to return the daemon process is running. And then if we wanted to return the stop function, we could just do DFX canister call daemon stop. And that says that the daemon is stopped. So that'll wrap up today's episode of the Internet Computer Developer Journey. If you enjoyed today's video, please be sure to like and subscribe to the DFINITY YouTube channel to stay up to date with all of the episodes of the Developer Journey and when they're released. Today's episode wraps up level 2 of the Internet Computer Developer Journey, which means the next episode will be module 3.1. And in that episode, we'll be talking about Motoko Package Manager, so be sure to check out that video once it's released. If you have any questions, be sure to check out the DFINITY Developer Forum. There will be a link in this video's description to the thread for the Developer Journey series where you can ask questions or give feedback. You can also leave a comment on this video or check out our DFINITY Developer Discord server for live chat with other developers on their developer journey. That's it for today. Take care.